Welcome, everyone. Thank you for coming to my talk about pushing Mongo. And this was the title as I wrote it in the abstract, but it's not that long. But I wrote the abstract quite a while ago, so since then, well, we didn't get around to using CSI, but we are going to talk about mutating webhooks quite a bit. And k8sbroker isn't really a thing anymore. That was this experimental thing, and it was very poorly and generically named. It's been since replaced by the SUSE folks with something called ArenaPercy, so we'll talk about that a little bit too. So there you go. There's the new title. It's even longer, sorry. So now that we've got the name figured out, my name is Julian Hjortshoj. I work for the CTO office at Dell EMC, but I'm also the PM of the Cloud Foundry Volume Services team. And when I was trying to figure out the abstract for this talk and what to submit, I went and Googled pushing Mongo, hoping to find some juicy quote about how this would be an idiotic thing to do and you shouldn't do it. It turns out it's not really a thing, except in the skating community, where pushing Mongo means kicking with your front foot instead of your back foot, which I guess, I'm not really a skater, so I don't really know, but this makes you look incredibly stupid. So, not what I was looking for, but I thought made a great metaphor for what we're doing here. We're going to CF push MongoDB and look foolish doing it. So with that in mind, with my colleagues, we've created this little Cloud Foundry app called Push Mongo, which is a CF pushable Mongo. You can use it with any Cloud Foundry. And what this thing is basically the Mongo binary, plus a little bit of start script that goes and tries to find where it should store stuff. And mysteriously, Mongo refused to listen on all IP addresses. And we didn't really know what IP address we were going to be. So rather than worry about why that was, we threw SOCAT in there to listen on all the IP addresses and port forward to Mongo. And that's it. So how does this work when we push it? So we're just going to go CF push Mongo. It's going to take just a minute. It's using the binary build pack, so it doesn't have to compile anything, which is nice. And then we're going to create a volume service. In this case, we're using an NFS service to a local server that we have co-deployed with our Cloud Foundry, bind it to our app, and then we're going to start it up. And this is using TCP routing so that we can address it directly. So once it starts up, we can just open a Mongo shell. So this is my local host. You can see it gives us some warnings about how it's listening on localhost because it doesn't realize that it's listening on everything. But we're going to add an entry. You can see we put something in with an ID of foo, and now if we find it, then you can see we stored it, so Mongo's working. Great, cool, right? But it's not really quite right? Like, what happens if we scale this thing up to 2? We're using a shared volume, which means everybody gets the same NFS share, which means we've got 2 versions of Mongo, 2 executables. They both want the same storage. So if I scale this thing, basically now you can see I have 2 of these things. It believes they're both running. If I connect to it, it looks like it connected, so okay. If I connect to it again, yeah. So we got load balance to the other one, and that one is sad. It's not starting up because of locks and junk. So there isn't really a good solution for this in Cloud Foundry heritage, or whatever we're calling it now, Cloud Foundry on Diego. Because we could kind of put some hacks in and say, oh, I want my second instance to use the instance index environment variable so that it stores its stuff in a different subdirectory or something like that. But Diego doesn't really give us any guarantees that it's only going to start one of our instances. Like, for instance, if you're deploying a new version of Cloud Foundry and your cell is evacuating, Diego is going to helpfully start up other instances on a different cell before it tears down your instances. Now you've got two instances. They both think they're instance index 0, and they're going to run into the same kinds of problems and data corruption and bad things, right? So also, shared volumes, NFS, SMB, those kinds of protocols are not very performant and not typically people don't use them for databases because they don't scale, they don't perform. So what do we need to solve this? We need single attach block storage. This is how all this stuff is typically laid out when it's deployed as a service. It's what Bosch does, for example. So to get that with Cloud Foundry, we need all of these things. We need Eirini, ArenaX, ArenaPercy, and that'll mostly get us there. So what are these things? But you probably know what Eirini is already, unless you've been asleep for 2 years or something. But Eirini is essentially an alternate scheduler that schedules Cloud Foundry workloads onto Kubernetes instead of Diego. RainyX is this cool new library. You can hear about it in depth at, I think it's like around 3 o'clock. The SUSE folks are going to give a better talk about it. This is the base library that allows us to add extensions to Eirini by installing these things called mutating webhooks into Kubernetes. And a mutating webhook is something that sits at the Kubernetes API and gives us the opportunity to take things that are just about to head into Kubernetes and twist them a little bit. And ArenaPercy is an instance of an RainyX plugin that intercepts pods and inserts persistent volume claims into the pods. And there's an associated ArenaPercy broker that when you bind a service to an app, will create a PVC and then remember the name of that PVC so that it knows what to inject into your pod when your pod starts up. So this sounds about right? This is what we need, more or less. Helpfully, our original volume service POC that we did back a year or so ago was using NFS. When the SUSE folks kind of pulled that out, teased that out, and built it into ArenaPercy, they, for whatever reason, switched it to use single attached block storage. So cool, one less thing we have to worry about. We've already got block storage. So we're good, right? No. So the problem, of course, is single attached block storage only attaches to a single instance. So if you scale this thing up, that mechanism is going to intercept the first pod in your stateful set when it starts up and attach the PVC to it. And that one will be cool. It has a block device. And then when you start up the second instance, unless you're just on a kubelet with only one worker, you get some error that looks like this, right? Kubernetes says, nah, you can't. You've got a single attached device. You can't attach it to 2 nodes. Well, that's too bad. So how does this normally work in Kubernetes? I mean, this is a well-established pattern, and people have started deploying their services to Kubernetes, so there has to be a way to do this, right? And there is, and this is kind of what it looks like. We, in Eirini, already use stateful sets, but this is also typically what people would use for a stateful application with multiple instances. And rather than a persistent volume claim, the stateful set has this thing called a volume claim template, which kind of means like, okay, we're not going to make the volume claims right away, but we're going to associate them to this stateful set, and you're going to use this template to spin up some volume claims on the fly as you scale out your stateful set. So if my stateful set has 3 instances, it'll create 3 volume claims, and it'll manage them and attach them in the right order and do all the good things. So for us, now we've got this ArenaX mechanism that allows us to mutate pods, but what we really want is to go mutate the stateful set, because we have to inject this volume claim template in. And so PVC is already too late, right? Because we'll have created 1 of it and we need 3 of it. So this is where the experimental part of the talk starts, and we started just kind of pulling wires out and dropping parts on the floor. We hacked around with RainyX so that rather than listening for pods, it's listening for stateful sets. We left it still looking for workloads in the CF workloads space. And then we had to, of course, change a bunch of interfaces. We then changed ArenaPercy so that it matched the new interface that has a stateful set instead of a pod. And we hacked that up so that anytime it sees a volume mount, it goes and puts one of these volume claim templates in. We didn't do the careful plumbing where you get to decide what that volume claim template looks like, but that's kind of exercise left for later. But the gist is we put this volume claim template in, and then inside the pod definition in the volume mounts, the name has to match. And then Kubernetes does magic things, and you get your block device nicely formatted with some kind of file system and good to go. And you can even specify the mount path. So how does that look when we run it? So this is, for background, Bosch deployed CF deployment with GKE running the Kubernetes and some wires connected. And let's see. Ooh, well, that's not helpful. So if we go look at the marketplace here, you can see we've got a nice ArenaPercy broker. We didn't actually change this, so it's still making a PVC when we create a service instance. We just don't use it because it wasn't really necessary for our experiment. So see, we've created a service instance. So now we're pushing Mongo. We're making 2 of it. So now we're going to bind the service instance here, just like we did before. And we're going to start it all up. So once again, this binary build pack doesn't have to compile very much. It starts relatively quickly. Keyword being relatively, everything is slower when you're giving a talk. If I'd been more assiduous, I would have pruned this pause out of my canned demo. But okay, so it's nearly started. And if I have another look at it, it's all started. So now if I go look in Kubernetes at the PVCs that have been created, and specifically the ones for CF workloads, you can see there are 3 of them. The one is the one that ArenaPercy broker originally created, and the other 2 are the ones that we're actually using that were created by the volume claim template. And of course, this being the Eirini version of Cloud Foundry, TCP routing is not working yet, so we can't really directly talk to Mongo the way we did before. But you can see here's my 2 running instances, and I can use kube control to get the IP addresses for those, and then because this is Google's cloud, I can get to my pods from anywhere inside that network. So, so in this case, we're going to just SSH into the router VM, which will then have access to that 10.44 network. This also gives us a nice way to control which Mongo instance we're talking to. So just grabbing that first IP address. Before I did this, I installed the Mongo shell onto my router VM. Of course, not a normal part of the router VM, but so here we're just connecting to that specific IP address, and then because we're talking directly to the pod, it's actually listening on port 8080, which is where Cloud Foundry wants it listening. So you can see here we're in the shell, so cool. We've got a database, we can insert something into it. So that's inserted. Now I should be able to query it again, right? So there it is. So great, one instance running. So what does the other one look like? So theoretically, we ought to be able to find our record here, right? So, no. So the problem here, of course, is we've got 2 instances of Mongo. They both have their own block storage. They're both relatively happy. They know nothing about one another, right? We haven't done anything. All we're doing is running Mongo. So they're not going to magically understand that they have a buddy. So, so to solve that, we need to set up a Mongo cluster, right? We have to somehow tell Mongo that it's running in a replica set, and here are your other things. So to get that working, we found this nice little sidecar process that somebody wrote in Node.js out there in the world. And because, well, I'm not positive, but I'm pretty sure sidecars aren't working in Eirini yet either. We just took this thing and glued it into our Mongo app and added a little scripting to get it started up and switched it to use the Node.js build pack so that it could go build itself and get all the things. Whoops. That is again not helpful. So we created a nice branch for this called k8scaled, which has this new sidecar process, not as a sidecar, but kind of inlined into it. And you can see here, it's using the Node.js build pack so that it can go get all the dependencies and do Node.js things in order to get this thing built. So if I push this one instead, then Mongo will start up, and we also had to change a little bit the startup string for Mongo so that it knows that it's supposed to exist in a replica set. But you can see here we're doing Node.js buildy things. does seem like there's a bit more flapping in this environment as apps are starting up. They kind of pop up and down a little bit. But here we go. We seem to be running. So now if I look at my pods and get my pod IPs again, you can see they've changed, right? Because of course it took my app down, started it back up again, so it created all new pods. But I can copy these into my paste buffer and hop back into my router VM. Oh. And this is the thing that I really should have trimmed out of this demo where I had a stray space in front of Bosch. So, going into the router VM, now I'm just going to have a look at these Mongo instances. And you can see, oh, now it knows it's a primary. So this is very exciting. It knows it's in a cluster. So now I should be able to insert something and go find it in the other instance. Okay, so cool. You can see it's now retrievable. So I have something nice. Now hopping into the other instance. This one knows it's a secondary, so should be able to get the things out of here. Nope. So this is just a Mongo active versus passive thingy, which we can get rid of by just telling it it's okay to talk to the slave, and then run the same thing again, and hooray, it worked. So that's it. So that's Mongo in talking to two block devices, working in a cluster, pushed by Cloud Foundry. Hooray. So, a few caveats. So this is dependent on stateful sets. There's been rumblings at various times about using replica sets instead of stateful sets. If we were to do that, then we wouldn't be able to use volume claim templates. So that could happen. This is also provisioning volumes at CF start time. So I'm starting up my app. The normal expectation in Cloud Foundry is that's going to be real quick. But now all of a sudden I'm doing this block device provisioning thing right in the middle of the start flow. It's not exactly ideal. Ordinarily, creating a service is deemed to be the slow thing, and starting your app should happen quickly. So it's a little hard to say that this is a problem for sure, but it seems like it could be a problem. It's something to bear in mind. The bigger disclaimer is that we're using mutating webhooks for this and for RainyX, and that's still a beta feature. It's kind of a dangerous beta feature that allows you to, essentially call into a void pointer and totally change what somebody asked you to do. And there's disclaimers on it saying that, like, the stuff that you do with your mutating webhook today might not be possible tomorrow because, we might decide that it was a bad idea after all. So maybe it's fine. Really requires TCP routing in order to work. which we don't have yet, but I'm confident that eventually that'll happen. And on the back end, we're doing this kind of reach around. The sidecar we added to go set the Mongo things up in a cluster is finding out about the cluster by calling back out into the Kubernetes API. And that for Cloud Foundry apps is kind of a no-no. You know, for starters, it's not really CF pushing if you're doing Kubernetes things after you CF push, right? I mean, we could just as well CF push something that does a kubectl apply, and also normally in Eirini when we're starting up pods, there's this auto mount service account token thing, which is set to false, which kind of says, yeah, we're not going to give you the credentials you need in your Cloud Foundry app to go talk to the Kubernetes API for what may or may not be obvious reasons. We, in our mutating webhook, just turned this back on to true and then went ahead and gave that default service account for the CF workload space, like permission to do everything in the world in order to get this working quickly. You probably don't want to do that. And ideally, if we were going to do this and actually make this work, we would figure out we'd get TCP routing working, and we'd figure out a Cloud Foundry native way for app instances to talk to each other, which shouldn't theoretically be very hard, right? I mean, this is kind of basic bread and butter stuff. But, you know, that's it for those are the only caveats. So just a few. So yeah, that's about the size of it. I think ultimately this exercise was less about Mongo and more about what if you have an app workload that maybe wants to do block device things or single attached storage things because you've got a lot of data. I think there's a lot of, less obviously wrong use cases that may still want to consume single attached storage. And I think that's one of the things that we're starting to think about as we start to think about, like, what does it mean to run Cloud Foundry on top of Kubernetes? What are those workloads that we couldn't really address before that we might be able to expand out into? So all of this delightful code that I've been showing you is available on GitHub. Both flavors of the Push Mongo app and then all of the various hacks. It's by no means production ready, or probably won't even work when you first pick it up because there's a few things hard-coded, but it's there to be played with if you so desire. And having said that, are there any questions?